Hey, welcome. So today we're going to tackle a classic math puzzle, one that seems impossible at first glance. How do you measure the area of a shape when it doesn't have straight sides? We're going to explore a really clever method for finding the area under any curve. It's called the Riemann sum. Let's jump right in. I mean, really think about it. If you've got a square or a triangle, no problem, right? We've got simple formulas for those. But what about a shape like this one, where one edge is just a flowing, unpredictable curve? How on earth could you calculate its area precisely? This is the exact problem that had people scratching their heads for centuries. So here's our game plan for this explainer. First, we'll really define the problem with curves. Then, we'll introduce the surprisingly simple solution using rectangles. After that, we'll build the actual formula, walk through an example step by step, and finally, we'll see how this whole idea becomes the foundation for calculus itself. Okay, so let's get right to the heart of it. The geometry toolkit we all learned in school, it's awesome for things with straight lines. But the second you introduce a curve, well, those old formulas just don't cut it anymore. A rectangle's area is just, length times width. Super easy. But the area under a curve, it doesn't have straight lines you can just measure. It's this irregular shape. And that means we need a totally new strategy, a way to handle the kind of infinite complexity of a curve. And the solution to this really complex problem is actually incredibly simple. It doesn't start with some new, scary formula. It starts with a shape we already understand perfectly, the good old rectangle. And this, right here, is the big aha moment. Instead of trying to measure the weird curvy shape directly, what if we just approximate it? We can literally fill that space under the curve with a bunch of skinny rectangles and then just add up their areas. Sure, it's not going to be perfect, but it's a start. And it's a really, really clever one. Okay, so we've got this great idea, but how do we turn it into something we can actually use? Do some math with? We need to get specific about how we create and add up these rectangles. This is where we actually build the Riemann sum. First up, how wide is each rectangle? We call the width delta x, or delta x. To find it, you just take the total length of your interval, that's from A to B, and you divide it by n, which is just how many rectangles you want to use. So the more rectangles you use, the skinnier each one gets. Make sense, right? So next we need their height, and there are a couple main ways to do this. For what's called a left sum, the height of each rectangle lines up with the curve at its top left corner. And for a right sum, you guessed it, the height matches the curve at the top right corner. This tiny choice is going to be pretty important because it affects whether our final guess is a little too low or a little too high. All right, enough theory, let's see this thing in action and make it real. We're going to estimate the area under a simple parabola, f of x equals x squared, and we'll do it on the interval from x equals 0 to x equals 2. We'll use just 4 rectangles to keep it simple. Let's kick it off with the left sum. First, our width, delta x. The interval length is 2, and we're using 4 rectangles, so 2 divided by 4 gives us 0.5. Easy. Our 4 left endpoints start at 0, then 0.5, 1, and 1.5. Now we just plug each of those into our function, x squared, to get the heights. Finally, we add up those heights and multiply the whole thing by our width, 0.5. And boom, the result is 1.75. Now, because our function is always going up on this interval, using the left corner for the height means each rectangle is just a little bit shorter than the curve. See that? It gives us a clear underestimate of the real area. Okay, now let's run it back for the right sum. The width is still 0.5, that hasn't changed, but our right endpoints are now 0.5, 1, 1.5, and the final boundary 2. We do the same thing, get the heights of these points, add them up, and multiply by the width. And this time, we get 3.75. So you can see the exact opposite thing happens here. By using the right corner on this increasing curve, each rectangle pokes out a little bit over the curve, which gives us an overestimate. So here's the really crucial point. Even though we don't know the exact area yet, we've successfully trapped it. We know for a fact the real answer has to be somewhere between our low guess of 1.75 and our high guess of 3.75. And this just shows you how powerful the method is. The exact area, which you can find using calculus, is actually 8 divided by 3, or about 2.67. And yep, sure enough, that value falls right smack in the middle of the range we just calculated. Our approximation totally worked. Now, real quick, before we move on, a heads up on some common mistakes. Always make sure you're summing the right number of heights. If you have 4 rectangles, you need to add 4 terms. And it's super easy to mix up your left and right endpoints. Honestly, just drawing a quick little sketch can help you avoid these simple slip-ups.
All right, for our final section, we're going to take this simple idea of approximation and build a bridge straight to the power and precision of calculus.
Think about it. Our guess with 4 rectangles was okay, but what if we used 8 or 16, or what if we used 1,000? As we keep increasing n, our number of rectangles, each one gets skinnier and skinnier, and those little gaps between our rectangles and the curve, they practically disappear. The approximation gets ridiculously close to the real thing. And this leads us to the ultimate endgame. What if we could use an infinite number of rectangles? Well, that is precisely what a definite integral is. It's defined as the limit of the Riemann sum as n, our number of rectangles, heads off towards infinity. This is the moment where approximation becomes pure exactness. So from now on, every time you see that big, loopy integral symbol, I want you to remember what it really means. You're just looking at the idea of adding up an infinite number of infinitely thin rectangles. The Riemann sum is literally the engine that drives integral calculus. And why should you care? Because this whole method of summing up tiny little pieces is how we solve major real-world problems. In physics, for example, the area under a velocity curve tells you the total distance a car traveled. In engineering, it can calculate the gigantic force of water pressing against a dam. And in economics, it helps figure out the total value that consumers get in a market. And that leaves us with one last thing to think about. This powerful idea of breaking down a complex, messy, curvy problem into an infinite number of simple, straight pieces is one of the most important themes in all of science and engineering. So the question is, what other impossible problems can we solve by thinking this way?